Today we're going to cover Mohr's circle, and some of the topics we'll be looking at are, understanding and sketching stress elements, using the appropriate sign conventions, appreciating why stress transformations are useful in the first instance, rotating the element using transformation equations, and building up to being able to sketch a Mohr's circle for a given stress element, using the Mohr's circle to find things such as the principal stresses, the directions, and minimum and maximum shear stresses, and finally also touching on the use of the eigenvalue method for the same purpose. So let's get started. Here I've drawn a stress element, and the stress element, in this case for a 2D stress state, is basically what stresses are seen by a point in the body. And what you can do is, once you have a stress element, you can label some of the stresses. So, let's go back here. So you can label some of the stresses. So you have sigma x in the x direction, sigma y in the y direction, and you have your shear stresses, tau xy, over here. So this is how you would label it. We have an xy coordinate system, so the stresses are given in x and y terms as well, and so this would be a basic stress element. There are some sign conventions to be aware of though, specifically when it applies to the shear stress. So if the shear stresses cause an anti-clockwise rotation of the stress element, then they are positive, so the ones on the x face on this element. And if they cause a clockwise rotation, such as those on the y face, they are negative. And so that's given here on the left hand side. And for the normal stresses, it's quite straightforward. Positive is tensile, negative is compression. So let's move on to the application of stress elements. Here I've just drawn a simple beam with an axial stress applied on it. And if you have this beam, it's very easy to imagine a stress element somewhere in the center, depicting the stresses acting at that point. In this simple example of an axial loading condition, you're just going to get sigma x's in the same direction to the applied global stress, and there's not going to be any shear stress or y direction stress. So that's pretty straightforward. But why is the rotation of a stress element or being able to do that important? So let's just delete that and have a look now at a case where, let's say you have a tiny crack in your beam that you've observed. And if we zoom in over here, you might know that a crack is more vulnerable in kind of the normal direction. So if you had your stress element like this, you might be interested in the stresses that are normal to this crack. So for this reason, you would need to orient your stress element so that it is aligned to this crack. And this is now done in a new coordinate system. So you're basically rotating the coordinate system. You're not changing the applied global stresses. So that's key to remember. And so this is why rotating and transforming stress elements can be useful. If we get to rotating a stress element in itself, one of the main ways you can do this is by applying the transformation equations. Now, if I just bring up HLT, you'll notice that we have the transformation equations provided, along with some details on principal stresses and principal directions that we're not going to look at the moment. But you have some transformation equations provided here where terms like sigma xx, sigma yy, tau xy refer to the kind of global coordinate system, and the values or terms which have primes in them refer to the inclined coordinate system. And in this case, it's inclined to an angle theta, which is defined in an anti-clockwise manner. And we've already said anti-clockwise is positive. So yeah, you can use HLT. So this is page 125 under solid mechanics and structures to use the transformation equations for this. So that's one way to do it. But obviously today we're looking at Mohr's circle. So we'll be moving towards that in a bit. One thing to note here is when you are rotating this stress element, if you were to rotate the element a full 180 degrees, you'll note, even though it's upside down, you'll note that you've basically returned to the same configuration that you had at the start. So that's one thing to bear in mind, because one of the most common questions students have is, why are angles twice the amount in the Mohr's circle compared to real life? And so this is one of the reasons, yeah? So a rotation in real life of 180 degrees returns back to the original stress configuration that you had sketched. Cool, so that's rotating the stress element. Now we get to principal stresses. So there exists an orientation of the stress element such that the shear stresses will be 0 at that particular angle, and the normal stresses will reach their maximum or minimum values. And these values of the normal stresses are referred to as principal stresses. And the angle, the orientation that is used to achieve this is referred to as the principal axes or the direction. So we can label these terms. So the principal direction is theta p, and typically you will number the stresses when they are principal stresses. So sigma 1 refers to in the kind of the x direction. I want to say x direction, but it's rotated, so that doesn't make much sense. But let's just say you have sigma 1 and sigma 2, where sigma 1 is typically larger than sigma 2. How does that apply to the Mohr's circle then? So what I've drawn on the left-hand side is just an axes system where on the kind of x-axis, the horizontal axis, you just have your stresses, normal stresses, and on the vertical axis, pointing downwards, because we're going to have the kind of inverse of the shear stress behavior. So the positive shear stress is in the downward direction. And what we can actually do is use the values in the stress element that I've shown on the top right to draw a Mohr's circle. The way you do that is you have your, let's consider the x plane at the moment, the x faces. You have a stress sigma x, which also has a shear stress tau xy, and on the x face, the shear stresses rotate the element in an anti-clockwise direction, so it's positive. And in our case, positive is on the bottom of this coordinate system. Similarly, so let me just label this very quickly. So you have sigma x, tau xy. Similarly, you can draw sigma y and negative tau xy. So negative will now appear on the top side of our diagram. So you have sigma y and tau xy negative, sorry, I should say. Once you have that, you can connect these dots to give you effectively the diameter of Mohr's circle, and you can carefully, not quite like that, but hopefully, oh, there we go, connect these so that you get your Mohr's circle. And this is obviously a useful thing to do, because now what we have done is diagrammatically, well, Mohr's circle has been quite badly drawn, but anyway, this is quite useful because you can diagrammatically obtain some of these key stress values, like your principal stresses and your maximum and minimum shear stresses. So clearly on the diagram, the maximum and min shear stresses are basically the top and bottom of this circle. And that is just going to be the radius, okay? So you'll have the minimum shear stress at the top and the maximum shear stress at the bottom. The principal shear stresses, remember, are when the shear stress is 0. And they occur at these 2 points over here. So the one over here will be sigma 1, and here is sigma 2. And these diagrammatically, geometrically, is basically the midpoint of the circle plus or minus the radius. The final thing that I want to talk about with the Mohr's circle here is the direction of the principal stresses, or theta p in the bottom right. So theta p is basically the rotation that would be required for your initial stress element to take it to the bottom stress element where there are 0 shear stresses. So on the Mohr's circle, that is basically this rotation here. And remember before I said a rotation in real life of theta is equivalent to a rotation of 2 theta on the Mohr's circle. Okay, so 2 theta. And that's all there is to the Mohr's circle. Now there is one other way to obtain things like principal stresses and the orientation of them. And that is by using the eigenvalue method, or the eigenvalue problem. So just a quick reminder, with the eigenvalues and eigenvectors, you can basically write this equation over here, where lambda I are the eigenvalues of the system, and the vectors ni are the eigenvectors of the system, and A is your matrix. So the eigenvalue problem basically rearranges this upper equation into the form shown here, moving the lambda n to the left hand side and equating it to 0. And this is quite interesting because then you can say that if your vector ni is not allowed to be 0, then the only way you can get a solution to this problem is if the determinant of the term a minus lambda I, capital I, multiplied by, oh no, we don't have that multiplied by, yeah, so let's ignore that. Yeah, effectively the determinant of this term is 0. Okay, so that's what we're looking for, and that's basically the eigenvalue problem. How does that apply to our Mohr's circle and finding out principal stresses and things like that? Well, you can refer to those terms in the eigenvalue problem, so things like I, lambda, and n, in terms of what we have in our continuum mechanics kind of scenario. So we have our 2D stress matrix, which is the matrix A. We have our principal stresses, which are the eigenvalues of the system. And we have our principal axes, or the orientation of these stresses, which are given by the eigenvectors of the system. Now with this in mind, you have basically 3 different ways, effectively, to solve a problem that has anything to do with transformation of stresses. You may use the transformation equations from HLT, you may use Mohr's circle, or you can use the eigenvalue problem as just described. So those are basically the key kind of points, key areas to do with Mohr's circle and the fundamental concepts. So just reviewing over the objectives, hopefully you feel like you've understood and taken in more and know a bit more about Mohr's circle and why it's used, how it's used. So I'm just going to leave this up and end the video now. Thank you.